Alright, so we're back into the intro slash revision. There's a bit of, we've covered some of this before in junior years, but we're going to do a bit beyond that now. And at the end, there's a big one, so be paying attention. Now, this is a long one, or longish. Again, we'll try to keep it under 10 minutes, but this is a longish one, so pay attention and take your notes. Just remember, pause, rewind, don't be shy. It's your pace. Okay, so we're talking about separation of mixtures today, and if you, we'll get our pen here, sure we'll get that one. If you look down here, these are the dot points that this video is covering now. The B's, the letters, they're the right hand column. It won't really cover those, except it will set you up for the experiment we'll do that follows this. Okay, so our goal today is to be able to identify the different separation techniques, and when you're given a situation, find the separation technique that is correct and outline how that would work and why that's the one. Alright, so with mixtures, they're impure substances, which means they have more than one thing in it, and basically they mean we can separate them by physical methods, not chemical. Okay, so there's one of the defining features that we can separate them by physical methods, and here are a couple of experiments set up, ready to roll. So this is really important, this phrase here. Whenever you see a mixture, I want you to think of that differences in properties. What is the difference in these two properties that we will use to separate it? That's how we do it. It's based on differences in properties, D.I.P. Alright, sieving is the first one. You know this, you've seen it before. The D.I.P is grain size or particle size, so we use the size of particles to separate solids from each other. Okay, and here is the standard one you've seen before. Here is, this one's from Ballarat out in the gold mines. That's an old-timey 1800s. It's called a cradle rocker, basically, and that you put the gold, all the chunks in here, and you shake it down, and all the dirt and stuff goes through. Here is a more modern version. So the gauge of holes, gauge means the size of holes, limit the size of particles that can go through. So if you are bigger than that gauge, you won't go through. And it's used in mining to separate the minerals from the gangue. Now, gangue, pronounced gang, but it's spelled like that. That's the worthless stuff. So remember, something is an ore if it has economic value. Otherwise, it's not an ore. It's just a rock. Even if it's got gold in it, if it's no economic value, it's useless. So the gangue is the stuff that's left over. All right. So magnetic separation. The D.I.P is the magnetic nature of it. Okay, so of the ore, and again, it's pretty straightforward. You can just separate iron minerals from within the ore, from the gangue, or in sand, you can use it to separate the ilmenite minerals from the rutile minerals, because one is magnetic, the other isn't. And basically, these are two ways it could work. It'll come down here, and the magnetic stuff holds on because the pulley. So the pulley is magnetic, so it just holds on until it goes past the pulley, then lets go, and you've got this barrier here to prevent anything from contaminating each other. This one, much more cool. So it all feeds in, and there's some magnets underneath the top conveyor belt. Again, another classic, the filtration, used to separate insoluble solids from liquids. Again, particle size. So similar to sieving, except the filter paper, and the filter paper does act as a sieve. It's fast and efficient compared to general sedimentation, which we'll talk about in a second. The residue, you need to use the correct terminology. Okay, so the residue is that which is caught here. Okay, and this stuff down here, that's the filtrate. All right, so now, one thing to remember is it's a good technique. When you're pouring in, once it's all filtered through, just to make sure you've got all of the filtrate going through, add some distilled water in there, just small amounts, squirt it in, and you should just get more filtrate through and essentially just leave the residue in the filter paper. Alright, sedimentation and centrifugation. So again, we're still talking about insoluble solids from liquids, but we can also use this for immiscible liquids. So that's two liquids that don't dissolve, and that's actually the example we have over here. Alright, so sedimentation, basically, as you can see here, the dense material sinks to the bottom, can be a solid or an immiscible one, and the top layer is then decanted off, which just means to be poured off. It's pretty simple. Centrifugation, similar thing, but instead of using gravity, you're using centrifugal forces. So you get your sample here, you put it in, and you just spin it around, and if you spin it fast enough, it will push the heavier stuff to the bottom while pulling the lighter stuff, the less dense stuff out. Remember, heavy is less to do with mass and more to do with density of something, Okay, so that's where we're at. So centrifugation, faster, more efficient, and to be honest, better for the lab. So heterogeneous mixture is, so two separate, not the same throughout, are mixed, spun at high speed, and the centrifugal forces pull them apart. And top layer is again just poured off, decanted off. So evaporation. So this is one way to get solid. And the DIP is density. The DIP here is the boiling point. So soluble solids from a liquid. That's where evaporation comes in handy. You've all done this before. Again, here is the technique. You just have a Bunsen burner under an evaporating basin and you heat it up. Now, we'll talk about good technique when we do this in the classroom. We're going to do a multi-stage separation soon. So it collects the solid solute. You often lose the solvent. The low boiling point is component, which is if you're doing salt and water, is vaporized, while the high boiling point one stays in the container. Now, boiling point of volatility, something is volatile if it has a low boiling point, and while water, we don't consider it to have a low boiling point. Usually it has a relatively low boiling point. Okay, again, salt and water is the one we often use, and where you see it is, so it doesn't have to be done with extra heat, it can be done with just the sunlight. And these are salt pans, and this is how salt is collected from the ocean. Alright, separating funnel. This is used for immiscible liquids. The DIP is density, and remember, immiscible means that they won't mix. Okay, so they form a heterogeneous mixture. The more dense liquid sinks to the bottom, as you can see. Again, this is so straightforward. Tap is opened, and you just pour the more dense liquid out. Alright, distillation. So this is for miscible liquids. Also, if you wanted to collect the solvent from a solid dissolved into a liquid, you could use this as well, and it would just collect the solvent down here. So miscible liquids, the DIP is boiling point again. This is going to be brief. So this is a physical process still, it's not a chemical process. That is important to remember. It's a homogeneous mixture of two liquids, so you put them in the round bottom flask here, you heat it up to the boiling point of the more volatile liquid, so the lower boiling point, and it will boil off up the column here, and it's got nowhere to go except down here, so it gets pushed down because of the pressure. And this here is what we call a condenser, and it has cold water running around the outside, and that will then cause the vapor to liquefy or condense and drip down into our Erlenmeyer flask or conical flask, whatever you want to call it. Both are correct. And here's the thing. Now, fractional distillation. This is the hard one. We have this little bit of notes here. So basically, it's cryogenic, which means it's done with. So cryogenic air separation is used for gases. Cryogenic meaning very cold. It is similar to standard distillation, and it's really easy to use. Not really easy. It is the standard one for air. The DIP is boiling point. Okay, So here's your diagram, and essentially this area here is all pre-treatment, and this is basically to get the gas, the air, into a liquid. So you've got liquid air down here, it's at minus 220. Now it gets passed into this chamber here. So if you look at these here, they are called button caps, and basically they're shaped like this. So a gas can come up and out like that, but it's very hard for if it turns into a liquid to drop back down that tube, the entrance tube. Alright, anyway, so this is a button cap. So basically the liquid air comes into this first column and is heated to all of minus 196 degrees, and it's very precise, and that's exactly where it's at, not any higher. And the nitrogen boils off. I'm boiling at minus 196 degrees, it comes up here and gets collected up here and is extracted out. Now it can be compressed again and liquefied and used to cool down here if you want, or used to cool down this section here, or it can be used for liquid nitrogen for storage of whatever you want. But basically that's where we get liquid nitrogen that we use down the ag plot or anywhere else. So now you've got liquid air, you've got oxygen and argon remaining. So oxygen boils at minus 183, which is a bit warmer than minus 186. Okay, so the liquid air is warmed just to minus 186, and then the argon comes out here and is extracted out. That leaves you with your pure oxygen. Now you can heat that up and pull it out here if you want. That works fine. Or some plants will have it just extracted out as a liquid. And that's how we separate the gases. Now, that's pretty much it, and we're going to end it there today because that's a lot. So we'll go to this next one. These are the things I want you to think about because you've still got a bit left to do before you come to class tomorrow. First, how would you separate a mixture of sand, salt, and water? Okay, this is a way that coastal cultures have gotten their salt. Now remember, you see it in the salt pans there. That's a good way of separating, but you still will often have sand mixed in with that. So how are we going to separate that? Jot down some ideas before you come in tomorrow. I want you to think about the limitations of each technique. None of these are perfect. They all have limitations. Now, there are two here we haven't covered. I want you to think about this before you come in and take some notes. This is where you take a bit of responsibility for it yourself. Crystallization. Find the difference between crystallization and evaporation. It's in your book, okay? Quickly knock up a table comparing and contrasting. So similarities, differences. Last one. Froth flotation. Again, it's in your book and it's used to separate solids. I want you to put together a quick diagram that shows how it works. I want it to be labelled, and I want you to write a quick explanation of it, including the D.I.P. That's it. Alright, stay rad, and I'll see you in class.